Hello, everyone. This is Muqi from Purdue University. Today, I will give you a talk about my paper, D-Helix, a generic decompiler testing framework using symbolic differentiation. Before talking about the framework, let's take a look at the decompilation process. The decompilation process can be basically divided into 4 parts. Given the binaries from the user, the disassembler will convert the binaries to the assembly code, and the assembly code will then be converted to IR by lifters. There are many IR languages. For example, LLVM-IR, P-code, which is used by Ghidra, VexIR, which is used by angr. After it, the decompiler will apply hundreds of heuristics on those IRs, and it will provide a lot of information. For example, type information. The printer will collect those information and then output the high-level language code, which is C code. However, during the decompilation process, semantic preservation is mainly overlooked. For example, we served 15 decompilers here, and then we find only 4 of them uses some semantic preserving heuristics. And most of those heuristics are only related with control flow graph. Also, we observe a lot of semantic inaccuracies in the decompilers. Some of those inaccuracies are easy to be detected. For example, in Ghidra, if we saw a symbol undefined, that means Ghidra cannot correctly recover that variable's type. There are still many semantics inaccuracies cannot be detected without testing. Also, during our survey, we find Decompiler is hard to debug because it has very large code base. Therefore, we propose D-Helix, a generic decompiler testing framework that can automatically vet the decompilation correctness. Let's take a look at the pipeline of D-Helix. Given the binaries, the lifter will give us the lifted IR, and the decompiler and the printer will give us a high-level language code. The first components of the D-Helix is RECOMPILER, which will recompile the high-level language code to a recompiled IR. After it, the SYMDIFF will try to extract the function semantic from the both IR to a bunch of constraints, which we call symbolic models here. And then the SYMDIFF will compare the symbolic models of different IRs. If the IR are semantically same, then it will just directly output the decompiled code. If it's not the same, we will use a third component, which is called tuner, to toggle the existing heuristic in the decompilers to generate the new high-level code, and then to recompile and verify it again. So here are some keywords for the D-Helix components. RECOMPILER is a component that uses the error log from the compiler to automatically and iteratively revise the code at the function level and generate the code to IR code. The SYMDIFF uses symbolic model to generate the SYMDIFF uses the symbolic execution engine to generate symbolic models, which I will show the details in next slides. And then it uses the symbolic models, uses SMT solver to verify the symbolic model at the IR level. The tuner will disable and enable the existed heuristic in Decompiler and try to find the problematic one. So here is how the symbolic models are generated. Given the source code, we run symbolic execution engine on its control flow graph and record its constraints from the condition and the return value. So you can see here from the bottom, we have the constant constraints to represent the return 1 and return 0. And then they will be nested by a if then else statement with the condition, where the condition is included as well. Now let's take a look at the evaluation. We evaluate D-Helix on 2 popular decompilers, Ghidra and angr. We test 56 functions from different projects and find 25 bugs, in which 17 of them are unknown. Here is a summary of the bugs we find by the SYMDIFF. We notice that around 80% of bugs we find by the SYMDIFF in Ghidra can be classified into 3 categories. 43% of them are function prototype recovery bug, 18% are literary value recovery bug, and 18% are type recovery bug. Similar for the angr, 40% is function prototype recovery bug, 20% is control flow graph recovery bug, and 20% is missing instructions. On the right side, it's the bug example, and we will talk about 2 examples in later case study. For the evaluation of tuner, we noticed that tuner can fix 16% of functions in Ghidra and correctly identified 4 problematic heuristics. Just recall what we said about tuner. It's disable and enable existing rules in Decompiler. So if the bug is not caused by the existing rules, for example, implementation bug, then tuner cannot fix it. However, tuner can still help developer to rule out some heuristic conjectures. Let's take a look at the first case study, incorrect usage of dwarf information. So basically, the compiler was given a function. The compiler will store the debug information in dwarf titles in the binaries. And the Ghidra will use this information to help recover, for example, the function prototype. Let's take a look at the first case. So given a function, compilers sometimes will make mistake in storing the dwarf information. For example, for here, it stores 2 different information in the dwarf in titles, but with different argument order. The Ghidra, therefore, will output the function with incorrect order of the arguments. When facing the function overloading, for example, for here, we have the function with the same name, but different arguments in one binary. The dwarf will also store this in 2 titles. However, Ghidra may fail to match the correct in titles, and then it will suspend its analysis, and it will give us argument with void. The third case is when the input is a structure. The compiler will basically pass the structure using multiple registers and store that there is only 1 argument for the function A in its dwarf in title. Ghidra cannot correctly analyze this, and then it will use the local variables instead of the input to represent. For example, for here in the condition, it uses the local variables, and in the source code, it uses the input argument, which is a structure. And all these 3 cases can be fixed by disabling dwarf in Ghidra. Now let's take a look at the second case, where the constant 128 is decompiled as -128. So notice in the source code, we have temp3 less than 128. And this statement will be lifted to 128 less equal to ECX in the lifter. The Ghidra will apply a rule named int less equal to convert this 128 less equal to ECX to 127 less than ECX. And in the next step, this is where the mistake happens. So basically, the rule subvary size extent will try to shrink the size of the constant from 32 bits to 8 bits because it stores the value 127. And it considers this value can be stored in a shorter constant. However, in the later process, Ghidra used some other rules to convert it back to 128. And the printing system in the Ghidra, because saw it's 8-bit constant, then it will print this 8-bit constant as -128. This issue can be fixed by disabling either rule int less equal or rule subvary size extent in Ghidra. And we have 4 more cases in our paper. So in summary, we propose D-Helix, a generic decompiler testing framework that can automatically vet the decompilation correctness. We find 25 bugs. And D-Helix is now open source. We want to thank the timely response from Ghidra and angr teams. We also want to thank our sponsor, NSF, ONR, and DARPA. OK, that's it. Any questions?